Good morning, everyone, and welcome to the second day for the Symposium for Quantum Undergraduate Inquiry and Discovery. We had a wonderful day yesterday, and we hope to have we hope to have another amazing day today. I'm Dhruv, one of the organizers for S.Q.U.I.D this year from the University of Maryland's Undergraduate Quantum Association. Co-hosting this session is Jade, LeShcack, another S.Q.U.I.D organizer and the president and co-founder of UMD's Undergraduate Quantum Association. Jade will be monitoring the chat streams in the back end, just making sure that everything goes smoothly. So if you see her in the call, that's what she's doing. As a reminder, our agenda can be found on our Discord server as well as on quantumcoalition.io/schedule. You can tune in via a YouTube live stream link on the Quantum Coalition YouTube channel or through the Zoom link posted in our Discord server. If you have any questions at any time, organizers will be monitoring the YouTube live stream chat, Zoom chat, and Discord server. We are starting off today with a keynote from our primary sponsor, Quantinuum. Our speaker for today is Dr. Mark Jackson, Senior Quantum Evangelist at Quantinuum, and Dr. Jackson has received his PhD in theoretical physics from Columbia University. Following that, he held many postdocs at many renowned institutions, including Fermilab. Now at Quantinuum, Dr. Jackson helps bring their platform to fruition. Please welcome Dr. Jackson. The floor is yours.
Thanks so much, Drew, and thank you to the other S.Q.U.I.D organizers. It's great to be here. So welcome, everyone. It's great to be speaking with you today. I'm very excited about some of the things that I'm going to talk about. So I think we have an hour planned for this. I don't think my presentation will last more than maybe 40 minutes. And so I'm happy to answer questions if anyone has anything. So let me now share my screen. And I think you should now be able to see that. Is that fine?
Yep.
It's working? Good. So it's a pleasure to be talking to you today and giving the industry keynote. So I realize this is probably a mixed audience with people from different backgrounds and levels of technical expertise. And so I wanted to start out by just kind of introducing quantum computing in general. And then I'll say some things which are more specific to what we do at Quantinuum, but I think that they're pretty representative of what's happening in the industry as a whole. This is a really unique time to be working on quantum computing because you probably know it was about 40 years ago that quantum computing was first suggested by Feynman in particular. And for about 30 years, it was purely academic. And only in the past 10 years or so has it really become commercialized. And now it's actually starting to get to the point where we think that there will be commercial applications very soon. And it's also starting to kind of enter the popular consciousness. This is a Time magazine cover from just a few months ago. And so clearly people are getting very excited about this. And you've probably noticed that quantum has snuck into things like Marvel movies even. And so there's a lot of quantum enthusiasts about this. But fortunately, I think most of the people here are pretty technical and you're going to be some of the experts. To explain why quantum computing is so important, I'd actually like to start by going back 200 years. So this is the first computer, as we would call it. It was developed by Charles Babbage in Cambridge, England. And it looks comically antiquated by today's standards. It looks like kind of an old-fashioned typewriter. But it actually has all the ingredients that we would identify in a computer because it has input devices and has output devices. And most importantly, it has switches. In this case, the switches are mechanical switches. But the key feature is that they're either on or off. So there's only two states. Well, we would say 1 or 0, but on or off. And we've obviously made a lot of progress in 200 years. So this is a picture of the computer that I'm running this presentation on right now. And it's much more stylish. It's incomparably faster. It's easier to use. But it actually has exactly the same features as the computer that I just showed you from 200 years ago. The switches are now called transistors. And they're much smaller and much faster, but they're conceptually identical. What quantum computing represents is really the first advance in human history in how we do calculations, in how we store the information and how a machine does these calculations. And so that's why this is so dramatic. To understand how quantum computers do this, so first we just remind ourselves that normal computers use bits, which are 1s and 0s. These are the switches that I just mentioned. And quantum computers don't actually use bits at all. They use quantum bits or qubits, we call them. And For those of you who are mathematically inclined, so I have a picture here, this sphere, this is called a block sphere, and this actually represents the configurations that a qubit could be. And so it could happen to be 0, and that's the North Pole there, or it could happen to be 1, and that's the South Pole, but it's free to be anywhere in between that, anywhere on the surface of that. And so you see there's a lot more parameter space, we would say. And one of the features of quantum mechanics is that things can exist in a superposition. That means that they can exist in multiple states at the same time. And that might seem a little counterintuitive, but if you think back to bits, which have to be either 0 or 1, a good analogy is thinking of it like a coin on a table. So a bit is like a coin on a table in that it has to be heads or tails, one or the other. But a qubit is like a coin spinning in space. So it could happen to be heads or tails, but it's free to rotate any direction. And so if it's anywhere in between that, we might say, well, it's sort of heads and tails at the same time. And so that's exactly like how a qubit behaves. It's not purely 0 and it's not purely 1. It's sort of in between that. And when you combine this idea with another concept called entanglement, which means the value of one qubit is correlated with the value of another qubit, there's a huge number of configurations that you can represent using just a few qubits. So one qubit represents 2 configurations, and 2 qubits would represent 4 different configurations, and 3 qubits represents 8, and so forth. Every qubit that you're adding doubles the number of configurations that you can represent at the same time. And so because of this quick scaling for the number of configurations, you can represent a huge number of configurations simultaneously using a rather modest number of qubits. And to understand why this is so important to us, this is a good example of what a quantum computer can do. So on the upper left-hand corner, this is my favorite molecule. This is caffeine, and it has not so many atoms. It only has 24 atoms. And we know how to simulate this. We know what the equations are. We've known for about 100 years. But if we were to put these equations on a computer to solve, we would need a very large computer, about 1 to 10% of the size of the Earth. So in principle, we could do that. It would just not really be feasible. But if we were to make a larger molecule, if we wanted to simulate, say, penicillin, we know exactly what the equations are, but trying to solve them would require a computer about the size of the universe. So even in principle, we couldn't do that. Now, in contrast, it's only a very modest number of qubits that we would need on a quantum computer, only a few hundred. And so that's why quantum computing is so exciting. It's not just that this is a incremental increase in the power of a computer. It's not like the iPhone 8 compared to the iPhone 7. This represents the ability to solve problems that we never even could have hoped to have solved before. And so that's why so many people are working so hard to build these quantum computers and the software. This represents some of the areas of research that will be revolutionized by quantum computing. There's a lot of related technology. So it's not just strictly quantum computing that will be affected. It's all these other areas, quantum algorithms, machine learning, chemistry, simulations, quantum communication, and so forth. And I'd love to spend weeks talking about all of these types of things. Unfortunately, I only have a few minutes, so I'd like to kind of focus on the things that I think are most short-term and most relevant to the people here. Because this is an industry keynote, I wanted to say a few words about how quickly the field is developing. So this is a snapshot of just a few of the companies involved in quantum computing now. And so you'll see that you'll probably recognize many of the logos here. Just 10 years ago, there were maybe 10 startups in the Western Hemisphere, between the Northern North America and Europe. And so this is how quickly it's grown. And so you'll see very established companies like Google and IBM and Microsoft in there. You'll see startups in there. And then, of course, there's still academic research going on. But the fact that things have grown so quickly and it's already become kind of specialized shows how much promise we think there is in quantum computing. This is what a quantum program looks like if you haven't seen it before. And so you see it's completely different from how we would program a normal computer. The way that you would interpret this, so we call this a quantum circuit. Every horizontal line here represents a qubit, and you read it from left to right. So on the left-hand side, this is the initialization of the qubits. So the qubits are usually initialized to the 0 configuration because that's simple and it's known. And then these colored blocks represent operations acting on these qubits. So sometimes the operations are just acting on one qubit by themselves, but you'll notice that sometimes the operations involve two qubits. There's sort of a line connecting them. And that's the entanglement, because it's saying, depending on what this first qubit is, you should change or not change the second qubit. And you may not know what that first qubit is, and so you don't really know how it's going to affect the second qubit. So you'll notice there's a correlation, even if you don't know what the exact value is. And so you have all these operations, and then at the end, you'll notice the qubits are being measured. That's that black operation with the needle there. And so upon that measurement, the qubit is forced to choose, is it 0 or 1? So until then, it can be in this crazy superposition and an entangled state. But when you measure it, the only result that you ever get is 0 or 1. So the output is, again, just digital, as with normal computers. The amazing thing is that these actually exist already. There are many groups who have actually built quantum computers, and there's even many different technologies that could be used to build these. So on the left-hand side, this is an example of a machine built by IBM, and you'll notice it kind of has this chandelier type appearance to it. The quantum computer is actually just a chip at the very bottom. But the rest of that chandelier structure, that's to control the chip. So you have the wires in there to actually tell the quantum computer what to do. And the different layers are because you have to keep the chip very, very cold. So it's actually contained in one of those cylinders filled with liquid helium. So you actually keep the quantum computer near absolute zero. And only at those low, low temperatures does the quantum computer have these special properties which you need in order to make the quantum computer work. Now, another approach is what's called ion trap technology. And this is an approach that we use. And this is a picture of our quantum computer. So this is actually in Broomfield, Colorado, near Denver. And I know it looks very Star Wars-y here, but this is actually what our computer looks like. So we use charged particles called ions, which we physically move around in our quantum computer, and then we change the value using lasers. So every qubit is a charged particle and an ion, and I'll say much more about that in a few minutes. So it's not just those two approaches. There are actually several approaches and several different companies exploring each one. And this is actually a fantastic thing that many groups are using different technologies, because there's no obvious winner. Every technology here has some advantages and disadvantages. So for example, superconducting, one of the advantages is that it certainly works, and it's actually, it's very impressive how quickly we can scale the number of qubits. IBM now has a 433 qubit machine, and they predict that by the end of the year, they will have 1,000, and the operations are very fast. But the downside is that the qubits are rather fragile, and you have to have all this infrastructure with the liquid helium to keep them very, very cold. Now, with ion trap technology, one of the advantages is that the qubits are very stable. We can get them to keep their coherence time, or retain their special quantum properties, for several seconds now. And the error rate is much lower, but it takes longer to do the operations. And so there's a bit of a trade-off there. And so similarly with other technologies which are being developed, every technology has an advantage and a disadvantage. And so there will probably be several winners depending on the type of problem that you're trying to address. So I want to go into detail a little bit with the computer that we have developed at Quantinuum. In fact, just about 3 weeks ago did we unveil this publicly, and this is called the H2 model. So the predecessor was the H1, and now this is the H2. And so you'll notice the H2 has this racetrack type formation to it. And right now we have 32 qubits. So there are 32 ions at any one time moving around. And this is an actual movie. This is not a simulation. This is an actual movie showing the ions moving around in this racetrack formation. So to say a little bit more about this, the fidelity is already getting very impressively high. So we can get the qubits to do what we want them to do with very high accuracy. So I've given the percentages there. So we're lowering the error rate as well as increasing the number of qubits. The progress that has been made is really extraordinary. I bet most of the people in the audience here have probably heard of Moore's Law, which has held true for several decades, that classical computers have doubled in power every 18 months or so. So 12 to 18 months, depending on how you're looking at it. And quantum computing has actually been on a much faster trajectory than that. So IBM came up with this term called the quantum volume, which is a single metric which encapsulates which can be used to estimate the power of a quantum computer. And we at Quantinuum have actually increased this by a factor of 10 every year for the past several years. And we believe that we can continue on this trajectory. So that orange line there shows the progress that we've made, each milestone in quantum volume. And just a few weeks ago, we announced the 65,000 something quantum volume. And just for comparison, in 2020, if we had started the Moore's law, you'll see, just for comparison, how slow Moore's law looks compared to the progress we've made in quantum. And so based on this trajectory, we believe that we could have commercial applications in just 2 to 4 years, which is really no time at all. I've actually been in this field for 6 years. And so if we could continue with the progress that we've made over the next few years, this will be really, really impressive. Companies will actually be able to use quantum computing for actual problems. Just to emphasize this again, this is a chart showing the progress compared to what we would use a classical computer for. And so we now see that we're starting to hit up against the point where we can no longer simulate things using a classical computer. Even benchmarking this computer, the H2 a few weeks ago, we started to encounter difficulty in benchmarking it. And so this is another indication of just how powerful quantum computing has become. So to say a few more words about what we do to build the quantum computer. So this is a graphic showing the previous generation, the H1, but the H2 is basically 2 of these with the corners at the end. And so you see that as the ions move around, it encounters these gate zones where the lasers can zap the ion and change the value of the qubit. We use ytterbium, if you're curious. These are ytterbium ions. So what happens is that we load the ytterbium atom into the trap, and then we ionize it. So then it becomes a qubit, and we can move it around. So we physically shuttle these ions around. And then when we want to change the value, as I said, we move it into this gate zone. So we can manipulate the qubit however we wish. And to do entanglement, so we have to put the ions on top of each other. So they're physically in the same place. And then we zap them together with the lasers. And so that creates this entanglement. And then we can move them around and do other things. So every quantum circuit is actually this very sophisticated choreography of moving the ions around and changing their value. And this is a simple example, this quantum circuit on the left-hand side. So this is 3 qubits indicated by the color. So you see that at time step 0, we initialize them. And then over on the right-hand side, this is what's happening on the machine itself. So time step 0, when we do the initialization, we use lasers to zap them all individually. At time step 1, we're applying the Hadamard gate to the red and the green. At time step 2, you see that we're entangling it. But before we do that, we have to physically move the green qubit over there in anticipation of what's going to happen, so that at time step 2, we can actually do this entanglement. Similarly, at time step 3, and then finally, we're measuring it at time step 4. We're measuring the green qubit. So you see that there's actually a lot of choreography that has to be done for these qubits, even for a very simple program. So we had to develop a whole subroutines just to develop what's the most efficient way to manipulate these qubits. These are some actual pictures taken of the qubit. So we've even developed some special cameras to peer inside our quantum computer, and that's what it actually looks like. So I've talked about H1, the previous generation model, and H2, which is what we have now. We actually have a roadmap spanning the next decade of where we want to go with this. And so we've already achieved the second milestone here. The next milestone will be H3, and it will look like a city grid. So you see it has all these intersections and junctions here. So the ions will be moving around sort of on these streets and avenues to get around, and then they can meet at the junctions. And so it's a much more sophisticated choreography that would have to be done, but we can accommodate many more qubits and many more interactions by doing this type of work. And the dream is, of course, to get this on integrated optics. So we have all of this on a single chip that we could fabricate and mass produce, and it would work at room temperature and would be protected from the outside environment and such. So that is what we were working towards, and we have every belief that we will achieve this by the end of the decade. Just to say a few more words about the progress we made. So we started, so the very first kind of prototype was called the H0. We started with just 6 qubits, and now we're up to 32. And by next year, that should increase quite a bit as well. So this shows some of the progress that we've been making. One of the big announcements a few weeks ago wasn't just that we announced the H2, it was that we were able to produce what are called non-abelian anyons. And for those of you who aren't familiar with this, so about 40 years ago, this famous physicist named Frank Wilczek, who went on to win the Nobel Prize for some other things, he suggested that certain particles could have this funny property where if you moved them around each other, they would pick up a phase in their wave function. So their quantum properties would remember how they've been moved around each other. And they could have any phase in principle. And so he called them anyons, sort of as a play on the words of the boson and fermion particles that we're familiar with. And a few years later, in 97, Kitev, who's now at Caltech, he realized that one type of these anyons, specifically non-abelian anyons, would be fantastic for building quantum computers, because you could have this braiding pattern which encoded information, and if you had any sort of outside noise causing errors, that would basically be irrelevant, because it's only the braiding pattern, these large movements, that would be important to the quantum computer. And so in 97, he realized that this would be a big step towards making quantum computers if we could do this. And so that's why some groups, including Microsoft, have spent many years trying to build these with different approaches and such. And so we're very proud to say a few weeks ago that we actually used our machine to achieve this. So we did a special type of these. So the non-abelian group was Z4, for those of you who know a bit about this. And so this is an article that we published. This was a collaboration with Harvard and Caltech, but they did it on our machine. And so we're very proud that we did this. And if you're curious about the technical aspects of it, I encourage you to read that article. So I next want to say a few things about software. So one of the aspects of quantum computing is, of course, there's not a lot of standards right now. There are several different groups using approaches, which is fantastic, but it can be a bit of a headache when you're trying to run your software on different machines, because the machines are all different, and even the software that's been developed by different groups is a bit different. And so that's why we at Quantinuum, we developed sort of a universal quantum software development kit called TKET. So TKET allows you to use any existing hardware to run your software, and you can move it around seamlessly. And so the way that TKET works, and I want to also mention on this slide, at the bottom of the screen, you show it's actually been downloaded over 900,000 times as of today. So this is a very popular tool. And to explain why, so what you do is, so TKET, you can download and you can use with the Python interface. So you write your code, and you can write it in Qiskit or Cirq or Quill or any such language. So you implement your circuit. TKET will first take that circuit, and it will first try to find a more efficient way to express it, because a quantum circuit is really just a big matrix, and you're using these gates to make up that big matrix. There's almost certainly a more efficient way of expressing that. And so TKET will go through different optimization routines, trying to identify how it can achieve the exact same circuit mathematically, but using fewer operations. So this means that your program will run a little bit faster, and it will be less likely to have an error introduced. And so once it does that, once it optimizes the circuit, then it will find the most efficient way to implement your circuit on whatever machine you're using. And it could be superconducting, it could be ion trap, it could be a simulator, it could be anything. TKET knows all the details of the different frameworks. And so it will take into account how the qubits are connected and the error rates, so that it can avoid the qubits with large error rates, for example, the coherence times, all of these details, TKET will take into account, so it will run your program most efficiently. And so at the end, you have your quantum application as efficient as possible. And so the great thing about TKET is that it's actually open source now. So even though we developed this originally for our own software, it proved to be so useful that about 2 years ago, we made it completely open source without any licensing restrictions whatsoever. So TKET is available on GitHub. You just download it and you install it. Again, you can use whatever quantum software you use. If you've already written it in, say, Qiskit, that's perfectly fine. You simply add one line saying, use TKET to compile this for such and such machine, whatever machine that you have access to. And so I would encourage you to use TKET if you're not already doing that. So I next want to talk about some of the applications that people are doing in quantum computing. And this is just a small subset. These are all examples that we have done with different companies. But the truth is that the killer apps probably haven't even been developed yet. It's smart young people such as yourselves who will probably think of some things that haven't even been realized yet. So one project that we did was with JSR Life Sciences and Crown Bio. So it's been known for some time that there's a correlation between the genes that someone has and how effective different drugs are. And one can do simple correlation studies on classical computers, but anything more sophisticated than that really doesn't work. The scaling is so bad that you really can't do anything more sophisticated than that. And so they came to us asking whether quantum computers could help. So we used some quantum machine learning algorithms to improve this. And so we believe this is a much more feasible way of doing this. We believe that we could find patterns in how effective different drugs are. So this was a study we did for different cancer drugs. There's a lot of interest from financial groups, especially in quantum computing, because a lot of what they do are these trading algorithms trying to predict how, say, a stock is going to behave in the future based on past patterns in this. And so machine learning tries to identify these past patterns and make predictions for the future. Many of these models depend on what's called Monte Carlo simulations. So Monte Carlo is a mathematical framework for modeling things that are either random or so complicated that they might as well be random. There's no way that you can understand the inner workings, such as a stock market. And the thing with Monte Carlo is that it has a very slow convergence. The more simulations you do, the more accurate the result you would expect, but it's very slow in how it converges. And one thing that people realized a few years ago was that there is a quantum Monte Carlo algorithm, which is quadratically faster than its classical counterpart. So that means you get the same level of accuracy with 1,000 quantum simulations as you would with 1,000,000 classical simulations, because 1,000 squared is 1,000,000. And so this was suspected for some time, and it was actually one of our researchers, Stephen Herbert, who proved this conclusively about 2 years ago. And so, we're very focused on these financial algorithms, and many banks are getting into this. You're probably aware that, for example, JP Morgan Chase has a very strong quantum group internally. So optimization is another thing that people are very excited about with quantum, because often in optimization, there's a huge number of possible configurations, and you're trying to find the one or the few which best optimize the system. And so a classical computer would have to go through every possibility one by one, and that can take a long time. Whereas a quantum computer can basically consider all of them simultaneously and try to identify the optimal solution. And so we've worked on a project with Nippon Steel on their assembly line process. So in their production plants and with their supply chains, this is a very complicated problem with a lot of moving parts. And so we found an optimal way to do this for that. And a similar problem was studied with Deutsche Bahn, the German rail group. We took a simplified version of their rail schedule and found a more optimal way to do it using quantum machine learning and optimization. So one thing I want to really emphasize is how real world these problems are. These are obviously simplified because quantum computers today can't handle the full version, but you see that we're already starting to look towards these real world applications. So I know in the beginning of my presentation, I said a few things about chemistry, but I want to go into a little more detail now. So chemistry is one of the things that was first identified as being useful for quantum computing, because it's very, very difficult for a normal computer to do these types of simulations. The equations that we get are quantum equations. They're strongly entangled, correlated, and so a normal computer has a lot of difficulty with this. This is a chart showing the trade-off between the accuracy that you would get in your calculation and the cost, computationally speaking. So if you only care about order of magnitude type answers, that's okay. You can do that very approximately for rather large systems. But as you want more and more accuracy, it's difficult to do that. And if you want perfect accuracy, what's called chemical accuracy, we can only do that for about 20 electrons right now. So using a supercomputer, you can only simulate a very small molecule. And the types of molecules that, say, pharmaceutical companies are interested in have tens of thousands of atoms and obviously far more number of electrons. And so there's no way we could even hope to do this using normal computers. Whereas quantum computers, we expect will be very efficient at doing this with perfect accuracy. So you see quantum computing sits there on the upper left-hand corner. And one problem in particular that people are excited about is fertilizer production. And I know that seems like an oddly specific choice of problem, but the reason that this has so much interest is because about 2% of the world's energy supply goes into making fertilizer. And it's a very inefficient process. It hasn't changed much in about 150 years. It's called the Haber-Bosch process. And we actually know that bacteria are much better at doing this than we are. We just don't know exactly how they do it. As I said, it's a very inefficient and expensive process, and it's bad for the environment. So we would love to figure out how bacteria do this. We know it has something to do with this reaction that I'm showing here, called FOMOCO. A few years ago, there was an estimate that we would need about 200 million qubits calculating for several months to do this type of calculation. And so that's a bit depressing. That's obviously not very feasible. But with just a few years of theoretical work, we were able to bring this down to about 4 million qubits calculating for 4 days. And even though that sounds still way out of reach, companies such as Google and IBM believe that they will have 1 million qubits by the end of the decade. And so it's entirely possible that we could be doing this type of calculation in the not too distant future. So one thing that we have been focusing on at Quantinuum is a quantum chemistry application called Inquanto, which distills about 24 projects that we've done into one application, which you run on your computer, say your laptop, and you would use it just like any other chemistry software. And so the types of calculations that a chemist would do, such as the ones that I'm showing here, these are all built into the application, and it sends the commands to our quantum computer to do the calculation and returns the result to you. But you don't need to know anything about quantum computing. You would use it just as you would with normal chemistry simulation software. And so, if this is interesting for you, I'd be happy to talk to you. We even have academic licenses for this. The types of projects that we have built Inquanto on are problems such as these. So we had a project with Total extracting CO2 from the environment using metal organic frameworks. Another project with Nippon Steel in which we were looking at the metallic structure, and then a project with Roche in which we were looking at a potential drug for Alzheimer's and how this interacts with our biology. And I've given the preprint articles here. So all of this is published and public, and you're very welcome to read up exactly on how we did this. The final type of thing I wanted to talk about is cybersecurity. And I know there's a lot of mystique about this. I notice in the media, there's a lot of emphasis about the close relationship between quantum computing and cybersecurity. And there is a good reason for this. When you use the internet, such as what you're doing right now, much of the time, sensitive information especially is being encrypted. So that means that a complicated formula is being applied to your data, such as your credit card numbers. And so this formula encrypts the data, it mixes it up, and that's what's transmitted. And then the receiver on the other end uses a key to undo that. So they use a string of numbers called the key to undo that formula. And most of the time, this works very well. When you hear about hacking, almost certainly it's because of a human error. It's almost never because this formula was directly undone. And this is because decades ago, about 60 years ago, when these formulas were being developed, they were purposely chosen to be so complicated that a computer could not undo them in any reasonable amount of time and effort. So it might take a supercomputer 1 million years to undo them, but that's hardly going to be done just to get someone's credit card numbers. And so to use a very popular type of encryption called RSA, it's the difficulty of factoring a number into the primes. So you've probably noticed at some time in your life that it's easy to multiply numbers together to get a big number, but going the other direction, taking a big number and factoring it into the primes, that's very difficult. You basically have to do guess and check, and that can take a long time. So most of the time, encryption works very well. Unfortunately, they weren't thinking about quantum computing when they did this. And that's understandable because no one had even thought about quantum computing. But in 1994, this very smart researcher named Peter Shor, he realized that quantum computers would be able to undo this very quickly, at least for this factoring type of encryption. And he actually developed the program. So this circuit here on the left-hand side, that's actually the quantum circuit for factoring a number very efficiently. And this chart on the right-hand side, this shows just how much more efficient it is compared to classical computers. So you see that the longer the key that you have, the longer it would take, and it's actually exponentially more difficult. So it would take a computer a long, long time to factor any key of decent length. But the blue line shows how quickly a quantum computer could do it in only polynomial time. It's actually cubic. And so that means that a sufficiently powerful quantum computer could basically undo encryption anytime they wanted to. And to show how vulnerable the internet would be, the top half of the screen here shows about 99% of encryption right now is vulnerable to quantum computing. So that this really is a very serious threat. Now, about 25 years ago, of course, the quantum computers, they didn't even exist. But the past few years, people have really started to be concerned about this. The good news is that people have started to prepare defenses against it. So the bottom half of the screen, these are what are called post-quantum encryption, or PQE type encryption methods. And so these are based on mathematics that we don't think quantum computers could undo. But we actually don't know for certain. There's a contest being done right now by NIST, this government agency. They invited people to submit different possible encryption formulas based on mathematics that we didn't think quantum computers could hack. And there were originally over 100 submissions, and then people investigated and did their best to hack them. And last summer, there were 4 winners announced, but within a few days, 2 of them were hacked. So we clearly have a bit more work to do before we declare an actual winner, which is completely stable against quantum computing hacks. One thing that I want to mention is that regardless of what happens with encryption or post-quantum encryption, you need a key to perform the encryption and sometimes to undo the encryption. And people often don't think very carefully about where these keys come from. They use what might be called a pseudo-random number generator, but this isn't random at all. There actually is a formula being used, and this has been exploited in the past. And so what we at Quantinuum have been developing is a way of producing provably secure keys. And that might seem too good to be true. How would you prove that a key is secure? And the way that we do this is we actually have a circuit that we run on our machine, which produces entangled qubits. And there's a statistical check that we do. So by doing measurements on these entangled qubits, we can verify that that entanglement is still there and that no one has been tampering or eavesdropping on this, because that disturbs the state. It destroys the entanglement. And as long as that test passes, then you can mix it with other sources of entropy and randomness to produce these keys. And so again, this is a provably secure way of doing this. And to explain how this statistical check of entanglement works a little more, imagine you had a source of entangled particles. So again, entanglement means that these qubits are correlated. They're random, but they're random together. So whatever one qubit is, the other one is. So these qubits, they're measured independently by 2 different observers, and we'll call them Alice and Bob. So Alice measures her qubit in some direction, and Bob measures his qubit in some direction, and each of them will get some answer, depending on the value that the direction that they're measuring it in. So they do this several times, maybe 1,000 times independently without comparing notes. And then after they're done, they do compare notes. And for the cases where they measured in the same direction, they should always get the same answer, because that's what the entanglement promises. And if that is indeed the case, Alice and Bob can begin their communication feeling secure, that no one is eavesdropping or tampering with this. But now let's redo this case where there's some sort of eavesdropper. So we call her Eve. So Eve is measuring one of the qubits, recording the value, and then replacing it. So if this were classical physics, this would be the perfect crime. We would have no way of knowing that Eve was doing this eavesdropping, because the system is identical afterwards to how it was before. But this is a quantum system. So Eve's actions have destroyed the entanglement. And so now when Alice and Bob do their testing measurements and they compare notes, even if they measured in the same direction, they will not always get the same result. Some significant fraction of the time, they will get different answers. And if that is the case, then Alice and Bob know that something funny is going on. So they don't proceed with the communication. They shut it down and they begin somewhere else. and do this testing. So this is a mathematical test that you can do to prove that things are secure. And so we do exactly this mathematical test for verifying that. I'm going to do this for verifying that these keys are indeed secure. And so now, there. So now, just to say a few final words about fundamental research that we're doing at Quantinuum. So we don't believe this has any commercial application in the short term, but we think that this is very important for getting quantum computers to have a general understanding and generalized AI. So you're probably familiar with natural language processing. If you've ever used Alexa or Siri or a chatbot or anything like that, you'll notice that computers can now understand what we say or what we type and understand what we mean by this and act on it. And of course, there's a whole mathematical framework for this. Computers have to understand why we put these words together in the way that we do and why we make these sentences and what we mean by this. And so a simple example, John walks in the park, this shows the different relationships between these words and how a computer would understand that. Our team at Oxford, led by our chief scientist, Bob Cook, has actually developed a quantum natural language processing. So this circuit that I showed you earlier in my presentation as an example, this actually represents John walks in the park as a quantum computer would understand it. And they've developed a whole toolkit called Lambec, which again is open source, for anyone to develop quantum applications based on this natural language processing. And so we believe this is still in its infancy, and this is just the first step towards general AI and things like a chat GPT on a quantum computer. And Bob has actually recently published this book, Quantum in Pictures, which replaces a lot of the complicated equations that we have to do, a lot of the circuits. He's actually developed this pictorial formation, which he believes is much easier for people to understand, especially those who don't have the mathematical background in quantum computing. And so again, this is available for publication. So that is it for my my prepared remarks. But of course, I'm happy to answer any questions that anyone might have.
Thank you so much for that lovely presentation. Very comprehensive overview of the field, as well as what folks at Quantinuum are doing. We have some questions lined up in our YouTube chat, but I guess before that, if anyone has any questions through the Zoom, we can take those before moving on to our YouTube questions. Okay, so while we wait, I guess the first question someone has is, some people may be nervous to professionalize in quantum computing due to worries about future job opportunities. You know, there's been a recent boom in quantum startups. But do you think industry opportunities will be long lasting?
That's a very good question, and it's certainly understandable. Whenever there's a boom, people worry about a bust, of course. The great thing about quantum computing is that the skills that you develop being in this field are easily translatable to other fields. Even though I have great confidence that the next several years will be amazing and that we'll continue to make progress with quantum computers, even if we do stall a bit, that's okay, because the technical skills in physics and computer science are easily translatable to other fields. In terms of the commercial sector, it's obviously not every startup will succeed. That's just how business works. But I think we're going to see a lot of consolidation in the next few years. I think a lot of mergers and acquisitions and things like this will happen. There have been a few examples. I think most notably us, actually. So Quantinuum began as Honeywell Quantum Solutions, the quantum division within Honeywell Corporation, and Cambridge Quantum Computing, a British startup. And our partnership over the past several years, it went so well that a year and a half ago, Honeywell Quantum Solutions and Cambridge Quantum merged to form Quantinuum. So we're our own company now. So that's an example of how like a hardware team and a software team can come together and everyone benefits. So I think we will see similar consolidation and acquisitions over the next few years.
Yeah.
Awesome. Can I ask a quick question? So, thanks for your talk. So I wanted to ask, as a quantum computing company, like how do you do essentially like quantum consulting? How do you find people with problems that can be solved? Because there seems to me that there's this issue where, you might know a lot about quantum computing, somebody else might know a lot about nitrogen fixation, making fertilizer or one of these problems. I mean, I'm speaking as someone who knows a little bit about physics and nothing about biology. So how do you connect with someone and say, oh, like we think our technology might be good for solving your problem, and get together with them and figure out a solution?
Yeah. So this quantum matchmaking, we haven't figured out the silver bullet for this. There's lots of approaches that have proved successful. It could be either like I speak at a conference and someone in the audience is interested in this and wants to learn more, and so they get in touch with us. It could be that that they have some problem that they can't solve using their existing technical their computers, and so they reach out to us originally. There's a variety of ways that we kind of originally get in touch. But once we are in contact, what happens is that they identify a few problems that they would like to solve and that they can't do using normal computing. And they speak with our scientists, and our scientists evaluate these in terms of how feasible it would be to do this with quantum computing in the next few years, and the potential payoff. If we were to do this, what would it mean? And so based on that, kind of that rubric of could we do it and how valuable would it be, we identify one or two problems that we would want to work on together. So the company has the expertise in that field, and we have the expertise in quantum computing. And so we've done this this collaboration dozens of times, very successfully. The instances in which it fails, I think it's usually because companies have an unrealistic expectation of what quantum computing is. I'd say that about 99% of the people I speak with outside of the quantum computing field, they have a misunderstanding about what quantum is. And what's funny is that there's two opposite misunderstandings which are popular out there. About half the people I speak with, they don't really think quantum computing exists. They still think it's like science fiction, and we've sort of made up these buzzwords. They don't understand that quantum computers actually exist already, that we actually have built them. The other misunderstanding is that people think that quantum computing is simply, it simply means that it's a faster computer. It's like a normal computer, but just faster. And so that they could take their existing software and run it on a quantum computer, and it'll just be a million times faster, and let's do that tomorrow. And so I have to kind of manage expectations on both sides. I have to explain, well, no, we have quantum computers. They absolutely exist. We absolutely have software, but it's only for very specialized applications. And we're still figuring out what those applications are, and it will take us time. There's been amazing progress. We think that we will have applications in maybe 3 years in some cases, but it will take us time to get there. It will take time to write the software and so forth. And so we're very sure to be realistic, so that there's no misalignment in expectations. So we talk with a lot of companies, and if we can come to an agreement, then we work on a project together. And depending on whether the company wants us to publish it, we do, and if they don't, then we don't. So we've had many projects. I just want to add one final thing. Quantinuum is actually kind of unique in that we don't do consulting. So we love working on projects with companies, but our goal is to build an application. We don't just advise companies on, here's what quantum computing is, here's a report so that you learn a little more, here's how you would get started. We don't want to do that. There's many other companies that do that. What we want to do is actually build applications and do things.
Thanks for that answer.
Our next question is someone in the chat. Skylar Chen has a question. So Skylar, if you want to unmute or put it in the chat, floor is yours.
Yeah, sure. Thanks for the wonderful talk. I recalled from the talk that you mentioned a collaboration with some drug design companies. I guess if you could talk just briefly a little bit more about, I guess, how that collaboration went, or the results, and if there's anywhere that I could look into this for further reading.
Sure. So the collaboration was with Roche, and it was examining a potential drug for Alzheimer's. So of course, the reason that a medicine works is because it interacts with our biology, right? There's a chemical reaction, and so that's what we want to understand, is how the molecules of the drug interact with our biology. And so this is what we studied. It was kind of a simplified version, but it was as realistic as we could make it. So we published an article about that. So if you email me afterwards, I'm happy to send you that preprint article. So we explain in technical detail what we did there.
Fantastic, thank you.
Yep. So another question we have, just looking at the chat, is what metrics kind of go into quantum volume, and is there a classical analog to that for traditional bits?
Yeah. So quantum volume is a metric that IBM popularized a few years ago, because until then groups would brag about how many qubits they had, as though that were the only indication of how powerful a quantum computer is. But that's very misleading, because even if you had 1 million qubits, if the error rate is high, then those qubits are useless. You can't do anything, because if you did just a few operations, then there's no point. You would just get garbage. And so IBM did a great service to the community by coming up with this term called the quantum volume, and it takes into account several different factors: the number of qubits, the error rate, the connectivity of the qubits, the coherence time, all of these things that are important. So they're all baked into this one term called the quantum volume. It's not simple to give the formula in words. There's articles there explaining exactly how this benchmarking is done, but there is kind of a simple way to interpret it. You can interpret the quantum volume as it's the number of idealized or logical qubits, of the number of states that you would get using that. So it's 2 to the n, where n is the number of logical qubits. So if the quantum volume is 8, it's sort of like you have 3 perfect qubits, even though physically, of course, you probably have many more than that. So the fact that we're now at 65,000, it's hard for me to do math in my head, is that corresponds to, I think, like 16-ish idealized qubits. So it's starting to get pretty impressive. And again, we have increased this by about a factor of 10 every year, and we believe we can continue with that. So in just 3 years, we'll be about 1,000 times more powerful than where we are today.
I see. So is quantum volume so when you say 16 idealized qubits, are those different to logical qubits, or are they the same?
It's the same as, yeah, exactly. It's the same as a logical qubit, yeah. The good thing about quantum volume is that it requires you to have both, for a high quantum volume, you need both a large number of qubits and good quality qubits. Just having one isn't enough. You won't increase your volume that way.
I see. Yeah, thank you for the answer. More in the chat. Oh, another question was, so earlier in the talk, you discussed the number of bits required for simulating molecules. And so the question is, how do you determine, how many bits you need, or how many qubits do you need for a particular molecule?
There is a formula. I don't know it off the top of my head, but yeah, every electron. So in a molecule, the things that are moving around that you need to keep track of are the electrons. So when we say that we're trying to solve the equations, what we're trying to do is figure out how the electrons position themselves to usually give the lowest energy, the ground state, and then you can figure out the other things. And so every electron is a degree of freedom, and so every qubit will represent that information. And so yeah, so as a molecule gets bigger, you have more and more atoms and more electrons, and it scales very rapidly. And so that's why we need so many qubits to do these types of calculations.
I see. Thank you. On that note, it's 10:56, so just about at the end. And so thank you so much for your time, this lovely talk, these questions. They've all been fantastic. For viewers, we'll be jumping into the second portion of S.Q.U.I.D for today, which is the presentation section. So you'll hear from some of our best presentations from the local chapters of S.Q.U.I.D virtually soon, so stay tuned.
Thank you, everyone, again. And I put my email there in the chat if you'd like to get in touch with me.
Perfect.
Great.
So much.
Have a great event. Thanks, everyone.
Thanks.